Alright, so a good portion of this week is going to be linear algebra review, and that's going to help us do a little bit more with Markov chains. So in general, we're going to have A is an n by n matrix. And for our work, that's always going to be the transition matrix. And then A times some vector is a scalar multiple of the vector. That's going to be the condition we're interested in. And if you remember from linear algebra, we call this vector v the eigenvector, meaning we can multiply on the left by A and get some scalar multiple of v, and we call lambda the eigenvalue. And we require that v be non-zero. This is just to make it interesting. If v were 0, then we would get A times v is 0, and then lambda could be anything. If v is non-zero, lambda has to be a very specific value. Okay, this is the same as writing A times v is lambda I times v, where I is the identity matrix, so all 1's on the diagonal, 0's everywhere else. And if I multiply that by lambda, that's all lambdas on the diagonal, 0's everywhere else. So if I multiply that by column vector v, that is the same as just scaling the vector v up by lambda. Now I can collect this all on the left and factor out a v on the right to get this equation. Things that are 0 are interesting. We can start analyzing. V is non-zero. So what does that mean? That means V is in the null space of A minus lambda I. In particular, A minus lambda I has a non-trivial null space. One of the things that means is that the determinant of A minus lambda I has to be 0. Any vector with a non-trivial null space, or any matrix with a non-trivial null space has determinant 0. And let's just look at an example over here. What do we mean by A minus lambda I? Let's just take A is matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A minus lambda I. Lambda I is just all 0's with lambdas on the diagonal, so it's going to be 1 minus lambda. We're just going to subtract lambda from the diagonal entries, and then every other number stays the same. That's A minus lambda I. So if I took the determinant of that, normally taking the determinant of a matrix produces a number. If I take the determinant of this matrix, I'm going to get a polynomial in lambda. For example, if I expand along the top row, one of the things I'm going to get is 1 minus lambda times the determinant of this minor. Determinant of this minor has the factor, has as one of the terms 5 minus lambda times 9 minus lambda. So that's going to get multiplied by 1 minus lambda. I'm going to get a third degree polynomial in lambda. Okay, so in general, this is a polynomial of degree n in the variable lambda. So what does that mean? That means it has roots. It might not have all real roots. It definitely has all complex roots. So the roots lambda 1 through lambda n are the eigenvalues of the matrix A. Why is that? Because those are exactly the numbers that create situations where determinant of A minus lambda I equals 0, which allow us to create this situation where this matrix has a null space and this vector is in the null space. Okay. And then we can find those corresponding vectors, v1 through vn. So let v1 through vn be the eigenvectors. We can find those as just vectors in the null space of that matrix. And then we can form these things. We can form this matrix capital lambda, and we're just going to put all the little lambdas on the diagonal and then 0's everywhere else. And then we can form this matrix capital V that's going to have these little v's as the column vectors, as the columns. Okay. Then we claim that A times V is equal to V times this matrix lambda. Why is that? Because both of these are equal to these things. We're going to have lambda 1 times V1 as the first column, lambda 2 times V2 times as the second column, and so on up to lambda n Vn. Let's just check that out. Okay, so what is V times lambda on the right? Then we're just going to have a lambda 1 with all zeros, go down. We are going to get lambda 1 V1 as the first column. You can keep checking. We'll get lambda 2 V2 as the second column. Okay, so that one appears to check out. And then what about A times V? Well, we're just going to take the vector V1 times all of A. That should give us lambda 1 V1. Vector V2 times all of A should be lambda 2 V2, and so on. Okay, so this checks out. These are equal. Okay, and what we would like to do, because we like capital lambda. This is a nice matrix. It's a diagonal matrix. Zeros everywhere else. We kind of like V, because we kind of know how to find the eigenvectors. What we don't like is A, because A can be any crazy matrix. I mean, we know that the columns will add to 1, but that's all we know about. It might be ugly. So, we want to try to get A by itself. How do we do that? We need to show, we need to basically take an inverse for V. That's how we'll be able to get A by itself. The only way we can do that is if V has full rank, which will mean the columns of V are linearly independent. So here's a claim that if the lambda i's are distinct, that means all the lambdas are different, then the VI's are linearly independent. Let's just take a minute to prove this. Okay, so suppose that the VI's are linearly dependent. What does that mean? That means we can find A1 through AN, not all 0, such that A1 V1 plus A2 V2 all the way up to AN Vn is 0. That's what it means to be linearly dependent. We can make a linear combination that adds to 0. Okay, we're going to take this equation and we're going to apply A, the big matrix A, on the left. So on the right-hand side, it'll be A times 0, which is 0. Okay, what happens to that? Well, it's really just, okay, let's write this out again. A1, V1, plus all the way to AN, Vn. And we're going to apply the matrix A on the left. That's going to equal 0 on the right. Then this will be A1 times A times V1 plus all the way up to AN times A times Vn equals 0. And then A times V1, remember, is lambda 1 V1. A2 V2 is lambda 2 V2. A times V2 is lambda 2 V2. Big A times Vn is lambda n Vn. Okay. We'll call that equation 2. We'll call the original A1 V1 up through AN Vn equals 0 equation 1. And now I'm going to take equation 1 times lambda 1. So that's going to be A1 lambda 1 V1 plus A2 lambda 1 V2. So all of them have lambda 1 here. AN lambda 1 Vn equals 0. We'll call that equation 3. and then we're going to take equation 3 minus equation 2. And what happens is the first term will cancel out. Everything else is going to be like in front of v2. Both of these are coefficients have a2. One of them has lambda 1, one of them has lambda 2. So it's going to be a2 times lambda 1 minus lambda 2 times v2, plus the next one will be a3 times lambda 1 minus lambda 3 times v3, all the way up to an times lambda 1 minus lambda n vn equals 0. And we claimed that all the lambdas were distinct, so none of these are 0. And the an's are not all 0. And they're still not all 0, because if they were all 0, then that would mean a1 was 0, which would mean all the an's were 0. Okay, so we have a linear combination now of v2 through vn with coefficients not all 0. And we can repeat this process. It looks like every time we do this process, we get rid of one of the v's. Okay, so we can repeat this process the next time we do it. If it's too confusing to look at these, just like replace this with b2 or something, b3. And then repeat this as if they were the a's. We can still generate new multiples of lambda by multiplying on the left by big A. Okay, so repeat this process. Remove a vector each time. And eventually, you're going to get, just the last, whatever the last one is, but if we do it removing from the front, we'll get vn by itself. Eventually, we're going to be forced to say that vn equals 0, which is not true. Because at the beginning, we assumed that all the eigenvectors were not 0. Okay, so that's a contradiction. So what this says, what was all this for? This was to say that v, which was v1, v2, all the way up to vn, now all the columns are linearly independent. So that means this matrix big V is invertible. And so then we had, we knew that A times V was V times lambda. So now that that's invertible, we can multiply on the right by V inverse, which means A is going to be V times lambda times V inverse. Why is this cool? Well, we were looking at powers of A. Let's look at A squared. Well, now this is V times lambda times V inverse times another V times lambda times V inverse. And V inverse times V is the identity matrix, so that collapses to the identity. And then I have big lambda times the identity is just big lambda. So now I have two lambdas basically next to each other. So this is V times lambda squared times V inverse. And I can do this as many times as I want. A to the n, same thing, it's a bunch of these next to each other. The V inverse and V, basically they cancel. They multiply to the identity. It's going to be big V times lambda n times V inverse. What's cool about this, remember that lambda was a diagonal matrix. Lambda 1, lambda 2, all the way up to lambda n, and these were zeros. Diagonal matrices are very easy to raise to the power of n. Just all the diagonal entries get raised to the power of n. V was kind of easy to write down, we said. Finding inverses is not too bad. Raising a random matrix to a big power is really hard. So this calculation, way easier than this calculation. And linear algebra helps us do that.